Dear students, in this class we are going to discuss about the multipass construction of shell and tube heat exchanger. Okay, multipass construction of shell and tube heat exchanger. Why multipass construction is necessary in shell and tube heat exchanger, or what are the advantages of it, or what is the limitation of single pass one heat exchanger, how to overcome it by switching on to the multipass construction. Last class we have discussed about the basic construction, basic design of the shell and tube heat exchanger, that is single pass one heat exchanger. Construction and working we have discussed in detail. Now why is it necessary to modify this design into multipass construction? That we are going to discuss. Here, if you just recall this single pass, as I already explained you, these two numbers, this indicates one is shell side passes, number of shell side passes, and this indicates this number indicates tube side passes. Okay. So in this design, both the shell side fluid and tube side fluid are single pass only. Here, if you just recall once, tube side fluid is entering here at this end, and after entering, this is the complete cross section available for this. So it enters all the tubes here, all the tubes. At a time it enters all the tubes and comes out of these tubes and will be coming out from the heat exchanger. And this is the tube side fluid. Only once it is flowing, entering, flowing through the length of the exchanger and leaving out. Only once it is flowing, tube side. That is why it is one. And here shell side fluid, here it is entering. After entering here, flows through the length here only once and then leaves. Here of course baffle, 25% baffle plates are there, that we have discussed in last class. Okay, so like this. So this fluid flows here, shell side fluid, both one. So what is the limitation of this? Limitation of this heat exchanger, limitation of 1 is what? Is relatively low velocities. Okay, relatively low velocities of fluids. Velocities of fluids. Both shell side fluid and also tube side fluid flows at a little lower velocities. Why little lower velocities? Tube side fluid enters here because after entering it occupies the complete cross section. Okay, because cross section is large here, naturally velocity will be less. Here also shell side fluid enters here larger cross section, that is why velocity is less. So how to overcome this limitation? So this design is modified into multipass construction. Then in the multipass construction, how is it modified? Is in this class we will just discuss what is multipass construction, how it will increase the performance of the heat exchanger. That way only we will discuss the actual multipass construction designs 1, 2, 2, 4 heat exchangers. No? In the next class we will discuss with the help of diagrams. Here why is it so important multipass construction, that only we will discuss. So here, because we are saying the velocities of both the tube side and shell side fluids are relatively low, then how we can overcome this? Increase the velocity. Okay, increase the velocity of fluids, both tube side and also both the tube and shell side. Okay, by increasing the velocities we can overcome this limitation. Then how to increase the velocity? That if you think, you can very easily guess that how to increase the velocity, what is the necessity of modifying the design. We can simply pump the fluids at higher flow rates. Simply we can think like that. That means pumping costs will increase. Simply if you pump the fluids at higher flow rates, what happens? Operating costs, pumping costs will increase. That means operating costs will increase. So without changing the pumping costs and without changing the length of the tubes, number of tubes, without changing anything of this design, then how to modify it to have higher velocities of the tube side and shell side fluid. That's our discussion. So before discussing that, we will recall first what is Q by A. This is according to McCabe Smith. I am using this notation, small q. Q by A is called heat flux. Heat flux is quantity of heat per unit area per unit time. That is heat per unit area that is transferred. How much heat is transferred from hot fluid to the cold fluid? That is heat flux. So how to increase this heat flux? As we know from the basics, Q by A is directly proportional to delta T Ln in the heat exchanger, shell and tube heat exchanger. In conduction you learnt what is that? In conduction, if you have a series of walls here, okay, then what is Q by A here is directly proportional to delta T. Here T1 minus T2. Okay, so these are acting in series. So what is the overall difference between T1 and T2? So if there is temperature difference, then only heat transfer takes place. If there is no temperature difference, there is no question of heat transfer. Okay, same thing applies for liquid also. Liquids also. Here we are treating liquids. So here two fluids, hot and cold fluids are there. So Q by A here delta T Ln we are using. This is LMTD, you know. So in previous classes we have discussed, that is in shell and tube heat exchanger we use LMTD because in the along the length of the heat exchanger delta T goes on changing. So that is why we take logarithmic mean temperature difference. Okay. So this proportionality constant is equal to Q is equal to Q by A naught U naught delta T Ln. This is the proportionality constant. This is proportionality constant. Okay. So U naught, this is called overall heat transfer coefficient based on A naught. Okay, based on A naught. Because you are choosing A naught here, we are using U naught. If you choose AI, and you will have to write here UI. Both A and A naught are for the inner pipe wall. Inner pipe wall. Okay. So we know this heat flux is equal to U naught delta T Ln. So any heat exchanger design, we need to have this as maximum as possible. Okay. Q by A heat flux should be as maximum as possible. So for this given temperature differences, then what should be increased? U naught should need to be increased. So what we understood now? If you increase U naught, Q by A naught will increase. So to increase heat flux, Q by A, increase what? U naught. That is overall heat transfer coefficient we need to increase. That we are going to discuss. How heat flux will be increased if you increase U naught. This is our point of discussion. Okay. How heat flux will increase if you increase U naught. So U naught, what is the equation for U naught? 1 by D naught by Di Hi plus D naught by DL bar into XW by Km bar plus 1 by H naught. This is the U naught equation. Okay, this is without fouling factors. Without fouling factors. Okay, so from this you are understanding that Hi and H naught are in the denominator. So D naught is the diameter of the tubes. So diameter of the tubes constant only. We can't increase now. The design is the particular design. We are not changing the number of tubes and all that. So XW is constant. D naught is constant. Thermal conductivity of the metal wall is also constant. Then what can be changed here? Only Hi and H naught can be changed. So U naught, increase U naught by increasing Hi and H naught. Okay. So if you increase Hi and H naught, this U naught can be increased. What is Hi? Individual heat transfer coefficient inside. Individual heat transfer coefficient for inside fluid. For inside fluid. Inside fluid is what here? Tube side only, no? Is it tube side? Inside fluid is nothing but tube side. What is H naught? Individual heat transfer coefficient for outside fluid. Outside fluid is nothing but shell side fluid. Okay. So here from this point, what we understood here, shell side fluid heat transfer coefficient and tube side fluid heat transfer coefficient. If you increase these two, U naught can be increased. Okay. If you increase U naught, then Q by A naught can be increased. So how to increase then Hi and H naught? That is the next question. Okay. Then how to increase Hi and H naught? That is the next question. Then in heat exchangers, in shell and tube heat exchanger, heat transfer takes place by which mechanism? Heat transfer takes place by which mechanism? By forced convection. By forced convection, because we are pumping the fluids through the heat exchanger at certain velocity. Some external force we are applying for the flow of the fluids. That is why heat transfer is taking place by forced convection. So in the forced convection, what is which equation do you use? For example here, or you know that NNU is a function of NRE and NPR. Okay. This is in forced convection. In forced convection we have this. For example, you consider the turbulent fluid. Consider turbulent fluid. Which equation do you use for turbulent fluid? We use Dittus-Boelter equation. There are many equations, Macadam's equation and all that. But one equation we can take, that is Dittus-Boelter equation. So Dittus-Boelter equation can be written like this: 0.023 into NRE power 0.8 into NPR power 0.33 into mu by mu W power 0.14. Okay. So this is the Dittus-Boelter equation. Now this is constant 0.023. And NPR is also constant. It depends only on temperatures, because properties. NPR is only properties. Cp mu by K. And these are also properties. So on which one NNU depends? NNU depends on, now for particular temperatures and all that, NNU depends on NRA. So NNU can be increased by increasing what? NRA. Okay? By increasing NRA. So what is NRA here? Rho dV bar by U. And here what? HD by K. NNU is HD by K. H means can be HI or H naught, anything here, okay? Depending on for which fluid we are calculating, we write HI. So if you write HI here, this D becomes DI, like that. So here D is fixed, diameter is fixed. These are the properties, depends only on temperature. So on the whole, here K is fixed, D is fixed. So H depends on what now? Here only velocity. Okay. So if you H can be increased if you increase velocity. That is the concept. Okay. So what we have understood here. If you increase tube side fluid here, velocity, HI can be increased. Increase tube side fluid velocity, then what will increase? HI increases. Okay? HI will increase. In the same way, increase shell side fluid velocity, H naught increases. So now we understood that by increasing the velocities of the fluids here, you can increase HI and H naught. Okay. So this, how can we conclude here? Increase velocity, H increases. You should remember one point here. Increase velocity. Velocity of tube side fluid, if you increase, HI will increase. Shell side, if you increase, H naught will increase. So increase velocity, H increases, both HI and H naught. Okay. Then what will increase? U naught will increases. U naught increases. Then what will increase here? Then Q by A increases. Okay. Because what? Q by A is equal to U delta T ln. So if you increase U naught, Q by A naught will increase. That is, heat flux will increase. That's what. So now you can compare with this. Q by A can be increased by increasing U naught. So U naught can be increased by increasing HI and H naught. HI and H naught can be increased by increasing velocity. Okay, from the back we have written here. So this is the concept. Why to increase the shift to multipass construction. That means on the whole we came to conclusion that we need to increase the velocity of tube side fluid and shell side fluid. Then automatically Q by A will increase. So the next question arises what? How to increase velocities of the tube side and shell side fluids. How to increase velocities of tube side and shell side fluids. Okay. This is the next question. So how to increase the velocity? For example, first take tube side fluid. Example, take tube side fluid. the basic principle we will use in the multipass construction to increase the velocity of the fluids is, you know that velocity increases, the basic principle which we use in flow meters construction and all that, eventually meter or a phase meter, basic principle is also this only. Velocity increases as cross section decreases. Okay, velocity increases as cross section decreases. This is the basic principle we use. We need to increase the velocity. Velocity can be increased by decreasing the cross section. So, for example, you take tube side fluid. Now, tube side fluid here, it is entering here. After entering here, the whole cross section is from here to here, shell inside diameter equal to, okay. Now, if you decrease the cross section available, that means by keeping a baffle plate here. Baffle plate is nothing but just a plate to divert the flow of the fluid. So here, if you keep one baffle plate here, then what happens? This cross section is reduced to half here. Okay, so because the cross section is reduced, here whatever the fluid that is entering, it flows with higher velocity into the tubes which are present in this part only. This fluid cannot enter these tubes. Only the tubes which are opened into this small part, into those tubes only this tube side fluid enters with higher velocity. Okay, that is the principle we are using. By keeping a baffling plate, we are decreasing the cross section. So, the velocity increases. Then, with higher velocity flows like this, it comes like this, then it flows like this. This with help of the actual diagrams we will discuss later on. Next class we will discuss 1, 2 and 2 for heat exchange. But this is the basic principle. So now here the tube side passes have become now what? 2 tube side passes. In the same way, if you keep one baffle plate here, then this will also become multipass. That means suppose tube side fluid after entering here, flowing once, okay, then taking turn, again flowing here twice. How many times it is passing? 2 times it is passing. So we are increasing the number of passes by keeping a baffle plate. The purpose of keeping baffle plate here is reducing the cross section. If you reduce the cross section, velocity will increase. As velocity increases, Reynolds number increases, and hence H will increase, individual heat transfer coefficient, and then overall heat transfer coefficient will increase and heat flux will increase. This is the basic principle. So we will discuss in the next class about these 1, 2 and 2 for heat exchanger. In these 2 heat exchangers, we have used this principle of increasing the number of passes by keeping baffle plates. Okay, this is why multi-pass construction is important compared to a single pass, but it has got its own advantages and disadvantages. Those things we will discuss when we discuss this 1, 2 and 2, 4. Thank you.